Hello and welcome to a presentation about how the deep reinforcement learning algorithms can help us in optimizing the networks. Imagine the neatly organized, modern, high-speed fiber network. But I don't mean modern as in what we have in our households or offices. Modern as in what Google or Amazon have in their data centers. While the throughput achievable by us, the mere mortals, can be measured in tens of gigabytes, Google's infrastructure is going up to tens or hundreds of terabytes per second. And do you know what is the bottleneck in a transmission like this? Because it sure isn't the fiber. The processing power. With data coming out of the interface in such amount, there is neither software nor hardware powerful enough to handle it. But there is a neat piece of technology that can help us. The machine learning. But we have to set the right course and stay committed. I'm an ICT graduate, a networking guy that grew interested in machine learning and wants to do some good combining the knowledge from those two fields. I've worked for 4 years as a programmer and switching to machine learning 3 years ago. Since about a year and a half ago, I've been working together with my supervisor, Professor Szymon Schott of AGH University of Science and Technology, on the project about applying deep reinforcement learning to Wi-Fi. And we think that this area of research is critically underexplored. Even using the reinforcement learning algorithms, which are ones of the hardest to train of the bunch, the gains in performance totally outweighs any difficulties in training, and it is often more stable than analytical algorithms. There is just no reason not to focus on using them for solving network problems. I'm going to speak for 20 minutes. First, I'm going to tell you about how the IoT can gain from deep reinforcement learning. Then I'm going to speak about the general benefits of DRL-powered wireless networks. And finally, I'm going to tell you about a small trick in our sleeves. IoT is a big niche, and it is only getting bigger. We are already making big changes in our infrastructure to accommodate those devices. The famous 5G is partially designed to make a full use out of the Internet of Things, and deep reinforcement learning also has some things to offer. One of the most persistent problems across all network communication is the channel access issue. I'm sure that some of you remember the bus network topology. Each device in the network was connected to the same backbone wire, and every single transmission had to pass through it. The problem is obvious. Only one device can transmit at a time, or something called a collision occurs. If the devices try to transmit a packet simultaneously, neither of them is going to get it right, and no data is going to be sent. This problem has been solved, or rather circumvented, in wired connections. Most of the Ethernet LAN networks now operate in another manner. Each of the devices in the network is connected with a dedicated wire to a centralized device called a switch that handles the simultaneous transmissions. However, the wireless connections have, well, no wires. Instead, the transmission takes place via radio waves of specified frequency. For example, the frequency can be 2.4 GHz, as is the case for Wi-Fi or Bluetooth, and then both the transmitter and the receiver need to be synchronized to the same frequency. Though there is a technique similar to the wire separation. It is based on channels, an idea that instead of using the whole available band for the transmission, we can separate small slices of the radio spectrum which can operate in the same time. If we, for example, split the spectrum into 12 channels, it means that we can have 12 concurrent transmissions which are not going to interfere with each other, more or less. There are some drawbacks though. The transmission speed will be a bit lower, the channels are a little bit overlapped, so there is some possibility of interference, but generally it's worth it, because it allows us for many more optimizations. But, well, the problem still stands. If two devices pick the same channel at the same time, they're out of luck. So the problem that we, as the station that wants to start a transmission, have at hand is choosing which channel to use and when. And now that we have defined the problem, we can look for a solution. I trust that all of us are familiar with the most popular deep reinforcement learning algorithms, but just for the record, let's do a quick recap. RL algorithms enforce a couple of rules on our problem. The most important of them being that we need to model it as a Markov decision process, which more or less means that we treat them as a game. We, as the reinforcement learning agent, are able to make some observations about the current state of the environment. For example, we can take a look at tic-tac-toe board and see what's happening. Basing on the observations or on the state of the environment, we make some actions. For example, we decide where to draw our sign, the circle or the X, so that we win. And what we long for is our reward, a point for us. And most of the time, once we state the problem, the fields fill themselves for us. So now, let's take a look at the publication that tackles the topic of channel selection. It's called Deep Reinforcement Learning for Dynamic Multi-Channel Access in Wireless Networks by the people listed here. Here, the agent's goal is to successfully transmit the packet as often as possible. At each time step, it will be able to choose one of n channels. It will define the actions. If the choice was right and there was no collision, we'll give the agent a reward of 1 point. Otherwise, a punishment of -1 will be given if the channel that the agent picked turned out to be congested. Previous attempts, along with the results, will compose an observation. The researchers have decided to use a Q-learning algorithm. Again, it is pretty much a classical algorithm in this field, but let's quickly go over it. Reinforcement learning agent, or reinforcement learning, or generally any dynamical programming algorithm, assume that every state that the environment can be in has to have a single optimal solution. So the idea is simple. For every possible state of the environment, we measure expected reward of each action, and then we select the highest one. However, for it to work, the actions must be discrete. We need to be able to choose one of n actions and nothing in between. And the problem? Well, the space of states as actions. If we try to implement it using a regular lookup table, then, well, good luck. While it is viable for some small dimensional problems, like for example the tic-tac-toe board, in the network applications, not so much. Considering that at each step we can sense one of, let's say, 16 channels, and each of them can be in two states, either congested or not congested, we keep a vector of 16 previous attempts. We'll need 2 times 16 to the power of 16, which is 10 to the power of 24 possible states, which is a ton. And then for each of them, we also need a record of all possible actions. And then we need to visit each of those options enough times for the algorithm to converge. But, well, the obvious answer is replacing the lookup table with some maybe universal function approximator, like, let's say, a neural network. And the states will now be the input of the network, and the output will be a reward expected for choosing each of the actions. And now, instead of a ridiculously large table, we have a simple pass-through neural network. The author stated that the reason why they chose the reinforcement learning approach was because it was challenging. The problem of multi-channel access has already been extensively studied using the standard approaches, but the DRL one has a tremendous advantage: its scalability. It shouldn't be surprising, because it is a recurring theme across the whole machine learning field, but this publication presents a direct comparison to analytical methods in the terms of computational power. An analytical solver of the algorithm took exponentially more time, analytical solver of the model took exponentially more time with each channel, and Eventually, it wasn't able to converge within time constraints for more than 5 channels. The DRL agent, on the other hand, had no difficulties with calculations for 16 of them. The authors then compared the results of the agent with a commonly used heuristics called Whittle index, and with the policy optimal to the tested setup. The optimal policy was created with full knowledge of the system dynamics so that it actually chose the best possible action at each point in time. And it turns out that the DQN agrees with the theoretical approach. It converged to the optimal policy, but it did so without the information about inner details of the network. The commonly used approach, on the other hand, didn't do so great. I've chosen this graph because it had the highest quality in the whole paper, but most of them look the same. DQN results overlapping with the optimal policy, and down below is the heuristics. Machine learning is rarely associated with energy conservation. When we think about neural networks inference, we imagine a huge supercomputer cluster standing in a server room that is using a small nuclear power plant worth of energy. However, there are a lot of projects that are aimed at conserving the battery power of the IoT devices. When it comes to IoT, the most common types of devices that we encounter are just gadgets. Smartwatches, smart light bulbs, smart speakers, maybe some air quality sensors that some of us have in our homes. There are mostly gadgets. However, where IoT really shines is other applications, industry or smart cities. In the latter, for example, they can be found in weather stations, the parkings, even lights for roadworks. But the problem is that they need access to power. We can go one of two ways. They can either be constantly connected to the energy lines, or we can give them some batteries. But when it comes to batteries, we are not yet done with the problem, because we need some way of conserving the power. Or maybe gaining some more. And this is where the idea of energy harvesting comes into play. There are a lot of sources of ambient power around us. The solar, thermal, wind, or even electromagnetic radiation that is present everywhere. We can harvest the power from pretty much any source, provided that we have equipment for that. But energy harvesting is not as easy as just staying connected. The ambient sources of power don't always have enough energy at their disposal to feed all the devices. We need to find a good balance between accessing the sensors or anything else that is connected to our device as often as possible and keeping the batteries charged so that we don't run out of juice. A publication called Energy Efficient IoT Sensor Calibration with Deep Reinforcement Learning is aimed at optimizing the battery use for a sensor with dynamic power requirements versus accessing and charging the batteries from some ambient sources. A dynamic power demand means that each time we access the sensor, the energy requirements for doing so may change, so that we aren't always able to predict what it will be our exact battery level after operating the sensor. In the presented publication, the agent was able to very quickly learn the optimal policy that yielded the maximum theoretically available reward. However, we also need to consider a distributed architecture. Imagine a network of sensors with independent ambient energy source, but with one central base station. The agent located there wants to have as stable stream of data as possible, and at each time step, it requests transmission from one of the controllers. Now, it can go two ways. If the sensor has enough battery power for the transmission, it will send the required information along with its energy level. However, if the battery is depleted, it will not be able to do so until it harvests enough power and we have lost time trying to communicate with it. A paper called Reinforcement Learning-Based Multi-Access Control and Battery Projection with Energy Harvesting in IoT Systems presents a solution to this problem. A deep reinforcement learning agent that tries to maximize the achieved throughput by polling only those sensors which it believes to have enough power for transmission. It's not going to be as easy as just trying the sensors one by one, though. This policy, by the way, is called round robin, and it was compared in this paper to the proposed one. Each of the devices has its own energy source, so the rate in which they are going to retain battery will be drastically different. The way that the agent works is by learning the patterns in which the energy comes back to the batteries. At each time step, the algorithm tries to predict the power available to each of those sensors and then chooses which one to poll basing on that data. And now I've promised you the Wi-Fi applications, and I am not backing out of this. One of the biggest issues in Wi-Fi throughput, aside from the physical layer issues, is also the medium access control, just with any other network devices. Here, however, it is a little bit more problematic. And why is that? Because here we don't have channels. Or rather, we cannot switch the channels dynamically, which is potato. It means that when we have multiple users, we need some way of forcing them to use the medium one by one, and the best way of doing so is random assignment. Wi-Fi takes advantage of something called DCF, Distributed Coordination Function. Its main principle is using a value called contention window. When a station wants to start a transmission, it first has to draw a random number between 0 and the current CW value. The station with the lowest number wins and is able to start the transmission as the first one. And how do the other stations know that? Because, well, the value means exactly how much time, measured in a unit called slot, does the station have to wait for before the transmission. So, for example, if you get a value of 8, it means that you have to wait for 8 slots. And if other station gets a value of 1, then it will start transmitting after the first slot, and you will be able to recognize it and just not start the transmission until it finishes. However, if two stations get the same lowest number, both of them are going to start the transmission at the same time, and at this point the collision is unavoidable. And, well, the more stations are trying to transmit at once, the more probable is the situation. But thankfully we've got full control over the CW parameter, so if the network gets congested, we can increase the window. However, this is tricky to balance. If the window is too large, then the stations can take unnecessarily long delays before transmitting, and if, on the other hand, it's too small, there are going to be frequent collisions. Together with Professor Szymon Schott of the AGH University, we have designed a system for CW optimization called C-Code, Centralized Contention Window Optimization with DRL. It allows for using any type of reinforcement learning agent and trains it in the task of selecting the right CW value. We have decided to showcase it using two algorithms, the aforementioned deep Q network and a deep deterministic policy gradient. The second one, DDPG, is one of the algorithms known as actor critic, but we are interested in it because of a nice quirk it has. It is able to operate using continuous values, unlike the DQN. What it means for us is that the DQN is able to select only values based on the power of 2, so 15, 31, 63 and so on, just like the default algorithm that is used in the Wi-Fi networks. However, the DDPG is able to use any integer between 15 and 1023 by default. The setup of the project is as follows. An agent is located in the access point, for example a wireless router. Periodically, the stations inform the AP of the number of frames that they have sent since the last update. The AP knows how many frames it has received, so it calculates current probability of collision in the network. Further calculations are based on the mean and variance of collision probability recorded since the last CW change decision. And then, basing on this info, the agent selects the CW value it deems to be the most appropriate. This change will be propagated to other devices in the network using beacon frames. The experiments were conducted in two scenarios. The first one, dubbed basic, sees a fixed number of stations transmitting at once, ranging from 5 up to 50. The second one, convergence, starts with 5 stations, and every few seconds a new one is joining. The results were compared to the standard algorithm and to the best possible result achievable for the standard approach. And for the basic scenario, the results are quite nice. For 50 stations, the C code was able to outperform the standard approach by nearly 50%. The TTP agent, which is not constrained by the power of 2, was also better than the optimal discrete choices. And the graph on the right for convergence scenario shows a run of a single experiment. Here, the number of stations steadily increases from 5 up to 50. While the performance of the standard approach is getting worse with every second and with each new joining station, the C-code agent is able to maintain it at a steady level, constantly keeping the network throughput high. So, to sum up, replacing the medium access control with a DRL agent drastically improved both the performance and the stability of the network. However, there is one small problem. Most of the publications I've mentioned were done only in simulations. This is a frequent argument raised by the skeptics, that machine learning is not efficient enough to work on devices with limited parallelization capabilities, which is the case for most of the network devices. Designing the hardware dedicated to a single algorithm is, while possible, completely not worth it in the long run, because of the limited updating possibilities. But, thankfully, the world of electronics has an answer to our problem. Reprogrammable hardware called FPGA. Intel, for example, is pumping a lot of money into industrializing this technology, and it is getting more and more attention from companies focused on networking. Because they not only offer better performance than GPUs, but they are also much better in the terms of energy efficiency. They are the types of circuits that will most probably be used for solving future issues with network performance problems. So, to conclude the lecture, reinforcement learning is a valid way of approaching the problems in the field of networking. These algorithms can offer us a giant boost in performance, keeping the energy requirements low, and there are still a lot of areas that haven't been explored. The physical medium will not be a bottleneck for much longer. Machine learning provides an extremely large and important potential for low-level optimization after breaking through that barrier. And this breakthrough is bound to be done. We can either be a part of this or not. So, what is there to do? Make your next publication about application of the deep reinforcement learning in network optimization. And when you finish lectures for today, pick up some article about network processing and think about what can be optimized there. It will probably take you about half an hour and just think what it can lead to. So, thank you for attention and see you at the Q&A.